Let's jump into implicit differentiation. So what is implicit differentiation and why does it work the way that it does? And that's what we're going to explore in this first video. A lot of students have some trouble with the why behind it, but are very good at the process. Process is not difficult. So the chain rule is alive and well in this process, and we're actually going to learn it and then use it in the next lesson in what's called related rates. So what is an implicit function? Well, to be implied means that you don't say something right out front, but it's kind of in the, it's an implication, right? So it's something that you're saying, well, it's assumed that that's meant. So if I look at you and I say, whoa, that shirt is nice. And I say it like that, you're like, well, he doesn't like my shirt. But if I say, whoa, that shirt is sick, even though literally I said that shirt is sick, what's implied is it's awesome, right? So there's implications there. So an implied function is one that is implied that the y values, or any of the values, are in terms of another variable. So it's implied here that y is a function of x, even though it's written so that x and y are on the same side together. That's what makes it implicit. X squared plus y squared equals 4. So again, you don't have x or y solved on their own. So it's not x equals, it's not y equals, it's implicit. And this is implicit, again, not x equals or not y equals directly. Here's a list of explicit functions. This is where we've been for a long time in math. Y equals a function. Very clearly, very explicitly, if I plug in x, I get out y. Right? Y is not jumbled up with it. Y has been solved for, and there's no other y's. This is explicit. Y equals the square root of 3 minus x squared. Right? So there's no other y terms. Y has been solved for. F of x is cosine of x minus 5 tan x. There's no confusion at all. F is a function of x. So how do we differentiate implicit equations with respect to x? That's the question. And that's what we're going to take a look at now that you know what implicit functions are. So way back in the past, when we differentiated with respect to x, that was what we've always done, right? You took d by dx of x to the fourth. And that with respect to x means that we were doing the normal rise over run with the normal limit definition of the derivative, and that leads to the power rule. And we would get 4x cubed. That was with respect to x. But when you derive something with respect to a variable that variable is not present in, you've got to slap on, as I like to say, a y prime or a dy dx or a d whatever by the thing that you're taking it with respect to. So this would be 3y squared, as you would think, and then the chain rule comes in times y prime or dy dx. So some people will write it like this, some people will write it like that, either way. Because we took the derivative of basically the y cubed part is the 3y squared and the inner function is y. And the derivative of y with respect to x is dy dx. So you could memorize that and say, okay, anytime there's a variable that doesn't match with what we're going with respect to, I've got to multiply by its derivative with respect to that variable. And you'll get the pattern of it as we go over more examples. But here's why that makes sense and why the chain rule is doing this. The implied part, this is implicit differentiation, is that y is actually some function of x. That's implied. So if we take the derivative of this, you get the derivative of the outside, using the chain rule, times the derivative of the inside. Oh, isn't that nice? And so you see that you have 3 times f of x is y, 3 times y squared, times the derivative of y with respect to x, dy dx, or y prime. So looking at it this way, with the implication in place, it makes sense how this is the chain rule and why it works. Isn't that cool? I think it's pretty rad. All right, so again, formally, always remember that the chain rule needs to be applied with implicit differentiation. Super informal is slap down a dy dx or y prime when differentiating an expression with a y in it. That's a memorization approach, but it does work. Okay, one last problem in this video. Let's put this to use. Find dy dx of x squared plus y equals 1. And I've given you a graph of, actually it's x squared plus y equals 2 is what that's a graph of over there. So x squared plus y squared equals 2. And we'll put that equal to 2, although it's not going to make much of a difference, to be honest. So it'll be x squared plus y squared equal to 2. And I might change up what these points are here, because these points aren't technically on the curve. So I'm going to change up these things right here. Anyway, the derivative of this is 2x plus, now you got something with respect to y, so that's going to be 2y times dy dx, or you could write it as y prime, doesn't matter. That's the chain rule, right? Because you're taking the derivative of y with respect to x. The derivative of a constant is 0. So if we're finding dy dx, we now need to solve for it. So I subtract 2x from both sides, literally treating dy dx like it is the only variable that we need to isolate in an equation. I subtract 2x from both sides. Now I divide both sides by 2y. So dy dx is equal to negative 2x over 2y. And the 2's cancel, leaving us with minus x over y. So what that is it's going to be, what is it going to be? The derivative function. So if I plug in x's and y's, notice we'd have to plug in x's and y's, we'd get slopes at points on this curve. And you know what, I'm going to go back and I'm going to call this x equals 1. Why not? Let's keep it x squared plus y squared equal to 1. And I'm going to write over this graph and say that should have been a 1, and a 1, and a 1, and a 1. Here we go. Find the slope of the tangent line to the graph of x squared plus y squared equals to 1 at each point. So each of these points are on this curve. In fact, 1/2 comma negative root 3 over 2 is going to be somewhere roughly like here. It's not perfect, but roughly there. I'll do that in a different color. We want the slope of the tangent line there. Well, to find that, you are essentially finding, and here's notation you might not have seen before, the derivative at 1/2 negative root 3 over 2. Well, we're going to take this point and plug it in here. Again, notice the derivative, the slope of this curve, is now with respect to both x and y. So we've got to plug in both x and y. And this is the notation. It means the slope, or the derivative, dy dx, at 1/2 negative root 3 over 2. So I plug in x, 1/2, and I put it all over negative root 3 over 2. So that'd be negative 1/2 times 2 over negative root 3, multiplying by the reciprocal, and that leaves me with 1 over root 3. Which makes sense. If you take a look at the slope of this line right here, it's not that steep, but it is positive. So there's the slope of that tangent line right there at this point. Let's do it for 1, 0, and it's really cool what happens. So the derivative again is minus x over y. So we're also finding dy over dx at the point 1, 0. Again, to find that, we're going to use our derivative. That would be minus 1 over 0. That's undefined. We've actually got a vertical tangent. Well, look at the point, 1, 0. What's happening at 1, 0? It's a vertical tangent line. Absolutely makes sense. So it really describes the curvature of this graph. Isn't that cool? I think it's pretty rad. So anyway, the whole purpose of all of this is to understand how to find the derivative with respect to a variable that isn't in the function at times. You got this. See you in the next video.